Here we go. We're ready for example number 5 on circles. Notice this time none of the information about we're not given the equation, the center, the radius. We're given an equation. All right, and the first thing would be that the x and the y are both squared, which is one of the characteristics of a circle. There's other things, but don't worry about it. We'll just keep it simple here. Now, here's the point though. They gave us an equation, but unfortunately it's not in the format that we need. The easy button is to have the equation look like this, isn't it? And if it looks like this, we've established that we can find the center and the radius very easily. The point is this equation needs to look like that. It needs to be manipulated. So here's the process we use to do that. First of all, I would say that we need to take the two terms that have x, which in this case are x squared plus 6x, and we're going to pull them off, and we're going to put a little gap here, because what we're about to do is what the math nerds call completing the square, all right? And so that would be a big deal here. Completing the square, all right? We got to make that, whatever. All right, now, there's a little formula here. We're going to talk about that in a minute. All right, in fact, while we're at it, let's do this. How do you complete the square? We're going to tack a number in that little blank there. And, well, before I do that, let me jump ahead. Let me do something else first, okay? We'll get into completing the square in a minute. I apologize. We've got the two terms that have x, and we're going to leave a gap here to complete the square. We're going to take the terms that have y and do the same thing. We'll have y squared plus 8y, and we're going to leave a gap to, air quotes, everybody, on the count of 3. Ready? 1, 2, 3. Complete the square, all right? And then I would advocate that we get the 11 out of the way, so let's add the 11 over to the other side of the equation. All right, so we group together the two terms that have x and leave a gap to complete the square. And then we've got the two terms that have y, and we're going to, ready, 1, 2, 3, complete the square. And then we move the 11 to the other side. All right, now let's get into completing the square. Sorry, I got excited. We're going to put a number in that blank, all right? And to calculate that number, we need to go, okay, when we put a number in there, that's going to create 3 terms, x squared, 6x, and the number, 3 terms, a trinomial, and won't the middle term end up being 6x? So as far as the x's are concerned, 6 would be the middle coefficient. Okay, that's what's meant by middle here. So to complete the square with the x's, if we apply that little formula there, we're going to say, okay, the middle, 6, if you put 6 over 2 in parentheses and then square it, that'll help you figure out what number needs to go in that little blank to complete the square. So 6 divided by 2 is 3, and 3 squared is 9. So we're going to put a plus 9 in that blank there, plus 9. Now what we always need to remember in math is that if you add 9 on your own volition to the left side of an equation, we introduced plus 9 here, didn't we? Then we need to add 9 to the other side of the equation to keep it balanced, right? The general idea, you can do whatever you want to an equation, most things. There's some exceptions to that. You can, if you add 9 to this side, you add 9 to that side. Okay. Now, if you apply that little magical formula, smart math people figured this out. Okay. So middle. So on the y's, the middle is 8. So if we apply that little formula there, 8 middle over 2 squared, middle over 2 in parentheses squared. 8 over 2 is 4, and 4 squared is 16, so we'll put a plus 16 in there. Oh, we just added 16 to the left. We better add 16 to the right to keep it balanced, okay? So it's all good algebra. As long as you add 16 to this side, do it to that side, everything is still equal, okay? So this side of the thing becomes 36. Now, by putting those terms, those numbers in those blanks, we created trinomials, didn't we? And when you see a trinomial, your instincts are usually to factor it, aren't they? So you factor that trinomial, and in this case, I hope you agree that that would be x plus 3 times x plus 3. Now, this is cause for excitement. Not only did it factor, but notice those are identical. And isn't another way of writing x plus 3 times x plus 3? Let's jump ahead next step. X plus 3 times x plus 3, that can be written as x plus 3 squared. And look at that, quantity squared. This is beginning to take the appearance of a standard center radius equation. Quantity squared. How lucky that that factored and that the two binomials were identical. Quantity squared. Squared. Isn't that exciting? Okay. Plus. So you look at this and you go, I hope this thing factors, and I hope they're identical, so it's quantity squared. I sure hope that happens. So you factor this one, and you go, well, that'd be y times y. How about we try plus 4, outer inner? Yeah, it factored. Y plus 4 times y plus 4. And you know what? That's y plus 4 squared, isn't it? So that can be written as y plus 4 parentheses squared. And if you notice, you look at this new equation and you go, wow, this looks like a center radius equation. Quantity squared plus quantity squared equals number. That would be an example of a center radius equation. X plus 3 parentheses squared plus y plus 4 parentheses squared equals 36. Boom. All right, that's why it's called completing the square, because popping that number in there completed this expression so that it would factor as two identical expressions, otherwise known as expressions squared. And popping that number in there completed that expression so that it factored into two identical quantities squared. Boom, there's your center radius equation. Yes! All right, now that we have that equation, it's a simple matter of graphing it, isn't it? So this would be very similar at this point now to example number 1, where once we had the equation, everything else fell into place. So the center here, all right, I want to take you back to the logic that we discussed before. Didn't we say, what would x have to be for that to equal 0? Yes, -3. And what would y have to be for this to equal 0? Yes, -4. There's your hk, right? Go plot that ordered pair. -3, -4. That'll be our center point for this particular circle. And then how big to make the circle? How far to travel, north, south, east, west? And again, that would be your radius. And just remember that that number on the other side of the equation is your radius squared, right? Again, squared. So you would hopefully look at that and go, well, you know what? The radius squared is 36. And so therefore the radius itself would be 6, wouldn't it? All right. Now I ask that you do all the work here in the wide open space and then just transfer only your answers into the boxes, please. You don't have to cram all the work into the boxes. Do the work elsewhere and put your answers in these boxes. And so if the radius is 6, we're going to go 6 units to the left of here, right? Count 6 boxes. 1, 2, 3, 4, 5, 6. I'm pretending, all right? And then go back to the center. 1, 2, 3, 4, 5, 6 this way. And then go back to the center and then count upward 6. 1, 2, 3, 4, 5, 6. I call it north, south, east, west. And then 6 downward, which doesn't fit. It's on the wall, but I'll put it here. And then, okay. See, isn't that beautiful? This is abstract art. As I keep saying, I have graph paper clear over there off screen. But this is a one-man show, I'm afraid, and I don't have somebody here to help me, pan the camera over there. So look, give me a break. Your circles will look way better on your awesome graph paper. But anyway, here would be an example again of a perfect circle, and, oh well.
What the? A perfect circle? Do it again. Show your process.
Well, first I draw this head. Then I erased some of the more detailed features. And 1, 2, 3, a circle thingy.
Wah, womp. Okay, so that's completing the square. We'll come back and do a couple more.